In this section, 8.6, we'll be looking at doing integration by using tables. And the key to doing integration using tables is to look in the table and find an integration that looks similar to what you're trying to integrate, to what the function you're given is. Um, there are 99 integration formulas given in our book, and we just have to find out which one is a match to the particular problem we're dealing with. So to illustrate that, let's do the integral of x squared over the square root of x squared minus 4 dx. So if we look at the integration tables, you'll notice that these are arranged in groups. We have a set here that has a constant plus a variable somewhere in it. We have some that have a quadratic polynomial in them, square roots of a constant plus a variable, a squared plus u squared, square roots of those. We have some that have trig functions. We have all sorts of formulas. So ours has a variable squared, or a variable minus a constant, and it looks like those could be squares. So if we look through these, let's see, here we have a set that has a variable squared minus, or could be plus, a constant squared. So notice ours, this and this match. So if we look down through here to 35, that looks like that could be similar to what we have. Now, until we determine exactly what our u is, then we may not know for sure. But once we pick our u and do our fit, our substitution, then we can determine for sure if it is the correct formula. So using this formula, our u squared would be x squared, which would make ux and du dx. Our 4 is the a squared, which of course makes a 2. So yes, this does seem to work, because notice this is du. We have a 1 on top. This is u squared. This is the square root of u squared minus a squared. So once we find out the proper formula, and we find our u and our a, then we just substitute into our formula to get our answer. So notice this formula works with u squared plus a squared, or u squared minus a squared. Since ours is minus, that's the bottom sign here, so we use the bottom one here and here. So ours is positive the square root of u squared minus a squared over a squared times u plus c. So that's our integral. Now let's do another one of these. Let's see. Let's do the integral of, let's do x, no, let's do 1 over x squared plus 4x plus 8 dx. So notice we have a quadratic in the denominator. So if we go to our integration table and look through, there is a set that has a quadratic in the denominator, and there are two different ones. There's one that has our variable on top and one that has a 1 on top. Well, it looks like ours may have the 1 on top. So if we pick that one, we'll take that, put it over here where we can compare. Now notice theirs is in ascending order. Ours is in descending order. So this is our A, B, of course C is 1. Our U is X, so DU is DX. So DU, 1, A, BU, CU squared. So yes, that's our the form we have. So the trick is, well, which one of these? Because we have two different variations that are similar, yet remarkably different. And one of them's arctangent, one's natural log. And the way we determine that is which one of these it applies to. So we need b squared. If we take our b is 4. 4 squared is 16. If we calculate 4ac, 4 times a times c, let's see, 32 is bigger, so our 4ac is bigger than our b squared. So we use the top one. So our integral comes out to be 2 over the square root of 4 times a times c minus b squared times arctangent of 2 times c times u plus b over the square root of 4 times a times c minus b squared, then plus c. So if we just do a little simplifying here, we have 2 over the square root of 32 minus 16, 32, 16, 32 minus 16 is 16. Arctangent of 2x plus 4, that's the same radical. 32 minus 16, so 16. Alright, we can reduce a little here. Square root of 16 is 4. On top here we have a common factor of 2, so we can factor a 2 out. Again, the denominator is 4. And lastly, we reduce, we have a 1/2 out front, arctangent of x plus 2 all over 2 plus c. So it's just a matter of substituting the proper things into our formula. Let's do another. Let's do the integral of x squared e to the x dx. Now this is something we have integrated by parts in the past, but there's also a formula that helps us with this as well. So if we flip through here, let's see. Notice here we have, let me zoom that in a little bit. We have u to a power times e to a power. So let's move this over. So notice we have our variable to a power, then e to our variable du, which is exactly what we have. So our u is x, so du is dx. Our n, notice n is that exponent of x, that's 2. So we have u to the n, e to the u, du. So when we integrate that, we get u, which our u is x, to the n, e to the u, minus n, times the integral of u to the n minus 1. Our n is 2, so n minus 1 would be 1, e to the x dx. So just like when we would have done that by integration by parts, we still are left with an integral. This formula just helps us break these powers of x down as we go. Notice we had an x squared, now we have an x to the first. So we can repeat this same formula. If we want to do this integral, our u is x, so du is dx. This time our n is 1. N is the power of x, so our n is 1. So I'm probably going to need more room than that. So this part integrates into u, which our u is x, to the n, e to the u, minus n, times the integral of u to the n minus 1. This time our n is 1. 1 minus 1 is 0. E to the u du. So before we finish this integral, let's get rid of our parentheses or our bracket. Let's distribute this negative 2, so that'd be negative 2 times the first term, negative 2 times the second. Negative times negative is a positive. Twice the integral. Anything to the 0 is 1. So let's see, I left an e to the x out here. So we have x squared e to the x minus 2x e to the x. That times that, so plus 2 to the integral of e to the x, which the integral of e to the x, the integral of e to the x is just e to the x, and then we have a plus c at the end because it's an indefinite integral. So there we go. Now some of these might be a touch trickier because sometimes they hide the fact of what our u is. Just a quick example. If we've got cosine theta over 3 plus 2 sine theta plus sine squared theta d theta. That does have sines and cosines in it, but if we look through our formulas that have sines and cosines, it doesn't look like any of them. Here are our sines and cosines. Notice that doesn't really fit any of those. But if we go back to a formula we used earlier, notice this is basically quadratic in form. We have a constant, a variable, or a function times a constant, and then a function squared. So essentially, on bottom we have a bu c u squared, which that would make our u sine theta. So du is cosine theta d theta. So notice all of that is du. So we have du on top, a bu, c u squared on bottom. We integrated one of that form earlier, this one. So we would just use that same formula, except this time our u is sine x. And of course our a, b, and c are different as well.